This is a brief tutorial on significant figures. First, we'll talk about precision and accuracy. Measurements that are close to the correct value are considered accurate. However, numbers that are repeatable, that is, they're close to one another, are precise. Precise measurements have more decimal places shown and therefore are more repeatable because your error will be in a smaller decimal place. Measurements can be accurate and precise, which is what we hope they would be. That is, the answer is repeatable and it is close to the correct answer. They could be precise but inaccurate. That is, the answers are close to one another but they're not close to the right answer. Good indication that perhaps your experiment is poorly designed, or they're neither accurate nor precise, meaning that you likely have sloppy lab technique. Using this sort of dartboard analogy, here the x's are close to the center, which we'll consider the accurate answer. They're close to one another, so they are also precise. Now here the x's are still clustered, but they're nowhere near the center, so they are precise, but they're not accurate. And here the x's are all over the place, they're not clustered, they're not close to the center, so they're neither accurate nor precise. So let's look a little more closely at significant figures. The number of digits that are reported in a measurement reflect the accuracy of the measurement and the precision of the measuring device. These figures that we know for sure plus one estimated digit is what we call our significant figures. Now, non-zero numbers are treated as significant. For example, that 1234 has 4 significant figures. Zeros that occur between non-zero numbers are always significant. That 101 has 3 significant figures. If I take that 0 out, I numerically alter the number. Zeros that occur before the first non-zero digit are not significant. Those are leading zeros. They're placeholders for the decimal. So 0.003 only has 1 significant figure. Zeros at the end of a number and after a decimal place are significant. Those are zeros of precision. 1.00 has 3 significant figures. Zeros at the end of a number, no decimal place, they're ambiguous. It's unclear how many they have. For example, 10,300, it's unclear how many significant figures it has. So those last 2 trailing zeros, it's unclear whether or not they're significant. The 0 between the 1 and the 3 is significant, so it could have 3 or 4 or 5 significant figures, depending on how many of those zeros are actually significant. It's common practice to assume those unclear zeros are not significant to avoid overstating the precision of the result. So by default, if you have no way of determining if those 2 zeros are significant, you would assume they're not and just assume 3 significant figures because you cannot state the significance of the other 2 to avoid overstating yourself. Now, numbers that are defined that way or numbers that are counted are considered to be exact. An exact number would have an infinite number of significant figures, although you usually don't display a bunch of decimal places. For example, if your average number, you're averaging 3 numbers, then you would add them up and divide by 3. In this case, the 3 is exact because it's how many numbers you averaged and is a counted number. Numbers that are part of a formula, a lot of your English to English conversions, your metric multipliers, which are just moving the decimal around, are considered to be exact. So let's determine how many significant figures the following numbers have. If I have 1,000, meters. Units don't affect the number of significant figures. It's unclear, but if we play to the least common denominator, you can only assume that one of those figures is significant. It's unclear whether the zeros are significant, so if you assume the least common denominator, you would have to assume one sig fig there. Moving on to the next one, 100.0 would have 4 significant figures, because the 0 after the decimal place is a 0 of precision. The next one, 0.00201 seconds, would have 3 significant figures. That 0 sandwiched in between is significant. The leading zeros are not. 2.401 times 10 to the negative 4th liters would have 4 significant figures, where that last number is in scientific notation, which is a convenient way to only show the numbers that are significant. Speaking of scientific notation, let's give a brief definition of what that is. It's a convenient way that is often used to express numbers that are very large or very small in a way that's easily read. Scientific notation consists of a number between 1 and 10, but less than 10, times a power of 10 to move the decimal place into the correct position. A negative exponent means the decimal is shifted to the left, where a positive exponent means the decimal is shifted to the right. Let's look at these numbers and express them in scientific notation. 0.00201. If I move the decimal place 3 places to the right, to go between the 2 and the 0 there, I get 2.01 times 10 to the negative 3rd. Getting that number back means I'd have to move the place back to the left, yielding a negative exponent. If I got a million, that's 1 times 10 to the 6th power. If any of those unclear zeros are significant, you could indicate that in the scientific notation. 0.000480 we write as 4.80 times 10 to the negative 4th. Notice I included the trailing 0 after the decimal place, but I omitted the leading ones. That makes it clear how many significant figures you should have. 52,000 is 5.2 times 10 to the positive 4th. Again, if any of those trailing zeros are significant, you could indicate that in the notation. Now, how do we use these significant figures in calculations? Calculated number must be rounded off to the correct number of significant figures. The rules vary, however, depending on the type of operation involved. You're going to round to the fewest number of total significant figures for multiplication and division. You're going to round to the fewest number of decimal places for addition and subtraction. If you have a logarithm function, you're going to retain the same number of decimal places as there are significant figures in the number whose logarithm is being found. Now, when you're doing the anti-logarithm, if it's a log base 10, it'll be 10 to the x, so natural log will be e to the x. The resulting number should have the same number of significant figures as the number whose anti-logarithm is being found to the right of the decimal. So you're going to look for the number of digits to the right of the decimal, and that's how many significant figures it will have. Now, how do you round that off? If the digit after the last significant figure is greater than 5, we're going to round up. If it's less than 5, we'll round down. If it's equal to 5, means it's equally distant from each, so we have to round that up and down half the time. So, what we're going to do is if it equals 5, we're going to round up if that number preceding that 5 is odd, and down if it's even. That way the 5 is rounded up half of the time and down half of the time to avoid skewing your results. So let's round each of these off to 2 decimal places to illustrate the rounding rules. 2.561 would just be 2.56. 6.849 will round up to 6.85. 7.465, since the number's even, we'll round it down to 7.46. 8.675, since the number preceding it is odd, we'll round it up to 8.68. Here we want to perform these calculations and round to the correct number of significant figures. If we have 2.0 meters plus 1.11 meters, we would get 3.1 meters, rounding off to the tenths place because that is the least precise decimal place. The next one, if we have 2.6 meters divided by 11.4 meters, we will get 0.23, noting that the meters cancel in this case. 2 significant figures, because 2.6 has 2 significant figures, 11.4 has 3 significant figures, and we round to the fewest significant figures. Log 2.56, we get 0.408, where in this case the number of decimal places is equal to the total number of significant figures in the argument of the logarithm. Last one, 10.643, we get 2.7 times 10 to the 6th, where the number of significant figures in the answer is equal to the number of decimal places in the exponent. If the operations are mixed, we want to perform the mathematics with more significant figures than are required and then examine the individual steps to determine where to round. So let's take an example of that and round it off to the proper number of significant figures. So let's take 2.6 times the quantity, 1.1 plus 2.64, all of that divided by 11.4, we get 0.85298 and some more decimal places. That's way too many to report, but we're going to calculating out to more places and then we'll worry about how to round it. Let's examine the steps. Look at each piece. We just take what's in parentheses. 1.1 plus 2.64 is 3.7, rounding off to the tenths place for a total of 2 significant figures. Take that answer and multiply it by 2.6. We get 9.6, which again is 2 significant figures. Take the 9.6 divided by the 11.4, we get 0.84, which was close to our original answer, but notice there's a little bit of rounding error, but it does help us see how many significant figures we need. Looking back at the original number, we'll round it off to the same 2 significant figures, and we would report our initial answer as 0.85. This has been a brief tutorial of significant figures.